Welcome everyone. In this video, I will be covering section 15.9, change of variables in multiple integrals. We used change of variables in double integrals by converting x and y into polar coordinates. We used change of variables also in triple integrals. We changed Cartesian coordinates to cylindrical coordinates. We changed Cartesian coordinates to spherical coordinates as well. The new variables r and theta, when we refer to polar coordinates, are related to the old variables x and y by the equations x equal to r cosine theta and y equal to r sine theta. And double integral over r f of xy dA becomes double integral over s f of r cosine theta, r sine theta, then you know that dA changes to r dr d theta in polar. Where S is the region in the r theta plane that corresponds to r in the xy plane. So the reason for converting to the new variables, either polar or cylindrical or spherical, is to make the integration process simpler. So you might have noticed that in some problems, the original region, when we converted to polar region, it became a polar rectangle, which was very easy to integrate because it made the limits of the variables r and theta definite limits. More generally, if we consider change of variables that is given by a transformation t from the uv plane to the xy plane. uv is a new variable, xy is the original variable. By the transformation t of uv equal to x comma y. By that what we mean is x is a function of u and v, and y is also a function of u and v. Where x and y are related to u and v by the equations x equal to g of uv, y equal to h of uv. Or as we sometimes write, x equal to x of u comma v, y equal to y of u comma v. If a transformation t is given by x equal to x of uv, y equal to y of uv, what is the Jacobian of t? The Jacobian of t is given by j, letter j, which is partial xy over partial uv, or dou xy over dou uv, which is the determinant, the second order determinant, partial derivative of x with respect to u, partial derivative of x with respect to v, partial derivative of y with respect to u, partial derivative of y with respect to v, which can be written as multiply across diagonally dou x by dou u, dou y by dou v, minus dou x by dou v times dou y by dou u. When I say dou y by dou u, it is partial y with respect to u. This is what the Jacobian is. Instead of remembering the rightmost side, you can remember like a determinant form, then it's easy to memorize. How do you change variables in a double integral? We change from an integral in x and y to an integral in u and v by expressing x and y in terms of u and v and writing dA equal to the Jacobian partial xy over partial uv du dv. In other words, dA is Jacobian times du dv. Thus, under the appropriate conditions, double integral over R f of xy dA becomes double integral over S f of x as a function of u and v, y as a function of u and v, times Jacobian partial xy over partial uv, the Jacobian times du dv. Here, R is the image of S under the transformation. How do you change variables in triple integral? Similarly to the case of two variables in part B, for triple integral, we have triple integral over R f of xyz dv is triple integral over S f of x. What is x? X is a function of three variables, u, v, w. And y is a function of three variables, u, v, w. Same way, z is a function of three variables, u, v, and w. So it is f of x, y, z. Then you need to have the Jacobian. Now the Jacobian is a 3 by 3 determinant, dou x, y, z over dou u, v, w, followed by du, dv, dw. Here, partial xyz over partial uvw is a third order determinant. Partial x over partial u. Partial x with respect to u. Partial x with respect to v. Partial x with respect to w. Then same way, partial y with respect to u. Partial y with respect to v. Partial z with respect to w. Partial y with respect to w. Partial z with respect to u. Partial z with respect to v. Partial z with respect to w. Let's try this problem number 2 for Jacobian. Find the Jacobian of the transformation x equal to u square plus uv, y equal to uv square. So the Jacobian is defined as J, which is partial xy with respect to uv. Partial xy with respect to uv, which is written in terms of determinant, 2 by 2 determinant, dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. We are given x equal to u square plus uv and y equal to uv square. So dou x over dou u, or partial x with respect to u, is 2u plus v. Partial x with respect to v is 0 plus u. Partial y with respect to u is v square. Partial y with respect to v is 2uv. So if we fill in these values into this determinant, we get 2u plus v. For dou x by dou u, dou x by dou v, that is u, then we have v square, then 2uv. Then if you multiply across and subtract, so 2u plus v times 2uv minus uv square, which is 4u square v plus 2uv square minus uv square. So it is 4u square v plus uv square if you combine these like terms. That is the Jacobian. There are some interesting observations about this change of variables. See, earlier we proved when we did polar coordinates, we know that x changes to r cosine theta, y changes to r sine theta, and then we also said in the double integral dA becomes r dr d theta. We in fact, proved this in a different way by finding the arc length and so on. Actually, we can prove this r is nothing but the Jacobian. So we will prove that the Jacobian for the polar coordinates for Cartesian to polar is r. So let's try, so the Jacobian for the polar transformation, the Jacobian is given by dou xy over dou r theta. Dou xy over dou r theta, which is determinant dou x over dou r, dou x over dou theta, then second row dou y over dou r, dou y over dou theta. They're all partial derivatives. X equal to r cosine theta. So what is partial derivative with respect to r? That would be cosine theta. What is partial derivative with respect to theta? That is negative r sine theta. Y equal to r sine theta, partial y with respect to r would be sine theta. Partial y with respect to theta is r cosine theta. We substitute these values over here. It's cosine theta, then minus r sine theta, Then in the second row, it is sine theta, then r cosine theta. If you multiply across and subtract, so it is r cosine square theta, then we'll have a minus and then minus r sine square theta. It is r cosine square theta plus r sine square theta. R can be pulled out. It is cosine square theta plus sine square theta. It is r times 1, which is equal to r. Thus, we have proved the Jacobian in polar coordinates simply r. Same way, it can be proved the same way it can be shown in spherical coordinates the Jacobian equal to rho square sine phi. In fact, in spherical coordinates, we know that x equal to rho sine phi cosine theta, y equal to rho sine phi sine theta, and z equal to rho cosine phi. We know that spherical coordinates, we have these. And we also know dv changes to rho square sine phi d rho d theta d phi. We can show that this part rho squared sine phi is the Jacobian. So we can try to prove Jacobian J, which in spherical coordinate is a 3 by 3 determinant, rho x by dou rho, which is actually, in short, you can write this as dou x y z over dou rho theta phi. That is a Jacobian. You can write that as a 3 by 3 determinant. Dou x by dou rho, dou x by dou theta, dou x by dou phi. This is for x, same way for y. Same way for z. If we find these values just the way we did for the previous polar coordinates, if we find out these values and substitute, it can be easily shown that the Jacobian would be rho square sine phi. You can try that as an exercise. In addition to these, there are some problems done in the videos for the section, which are problem number 17, problem number 23, problem number 15 from the additional suggested problems. You can see all these problems that are highlighted here in the videos for the section. Hope this video helps.